Right, log likelihood. The crucial thing in all of this is that in elementary statistics, you hold the hypothesis steady. I say, here's a coin with probability 0.5. I want you all to toss that coin 10 times and tell me how many heads. And we get 5 and 7 and 9 and 2 and 5 and 3. So we hold p constant, and the data changes because all of you generate your own data. And that's great. Likelihood is hard because we're doing the other thing round. In likelihood, we fix the data and vary on the x-axis the hypothesis. And that is a hard thing to do because your brain rebels against it. And it says, well, I don't know what p is. And I'll say, well, all right, then that means you're moving around this axis. So I've got off-pat answers to sort of questions about p being known or fixed or whatever. But it's a difficult thing to do because your brain says, well, where is it? It's here, somewhere. And it doesn't make sense. You've just got to turn your brain inside out because your data's fixed and your probability is changing. You don't know where it is. You want to maximize it so it's here. It's all because you're making inferences about an unknown parameter. It's hard. It's not particularly hard mathematically. This mathematics is not any harder than anything else you've ever seen, but conceptually it's a very difficult step. It's basically because of a contradiction between what happens when you know the true value of p, the data changes, and now I'm turning it completely on its head and saying what happens if we write the data down and keep it fixed, and we conceptually at least move p around. It's a very profound shift in thinking. It's a very difficult step. Okay. Having said that, I'm going to talk about something else. I'm going to talk about the Gaussian distribution with data x1, x2 up to xn. And I want you all to think while I'm talking that these observations can be observations about the temperature of your fish tank, or it might be the probability of you getting the question right, or it might be the proportion of your children that get the correct answer to an exam, or it might be what other projects have we got here? There's whole bunches of different projects. I want you to think about these observations from your project. And we want to estimate mean and standard deviation. Or variance. Mu and sigma squared. And again, what you've been taught to do up till now is I come up to you and I say, listen, here the mean is equal to 10 and the standard deviation 6. So go away and tell me what it looks like, and you plot this beautiful bell curve. That's what you've been doing up to now, yeah? And in fact, that's what I did, because I said, oh, look what happens if the mean changes. It moves like that, or it moves backwards. What happens if the standard deviation changes? Well, it turns it into, from a nice bell-shaped curve into a sort of sharper one like that. But the flow of information is very clear. I tell you what the mean is, I tell you what the variance is, and you produce for me this, this curve, and show me how it changes as these guys change. Now here's the killer. In practice, in your assignments, in your portfolios, you won't know what the mean is, and you won't know what the variance is. You have to estimate it. So I'm going to talk about the theory of how that works. Let me remind you what the Gaussian distribution is. Gaussian. The probability that x equals x. I'm writing slipshod over notation here. I don't want anybody to pull me up that I'm not using proper measure theoretic notation. I think one of the reasons I get confused is that in my line of research, I'm considering how this formula behaves on the complex plane, and so my square root, sometimes I'll forget to put the square root or a factor of 2 in. It's because in my research the 2's appear in different places. So it tangles me up, which is annoying. So what's the probability of observing x1, x2? Let's just put two observations, given mu and sigma squared. Let's just have a look at that, remembering that we don't know what these guys are in practice. Well, I'll just write the formula out, which might look a little bit frightening, but quite a lot of mathematics here. What I've done is just written out the formula for the Gaussian distribution for x1. And I've written the formula for the Gaussian distribution for x2, just making the casual observation that mu is the same in both of them and sigma is the same, or sigma squared is the same in both of them. All right? So that's quite nice. I can multiply them together because of a fact which I've forgotten to state. I can multiply because x1 and x2 are independent, which I covered in lecture 2, I think. x1 and x2 are fixed. Mu and sigma squared are unknown and vary. Okay. So this is a likelihood function. So we're going to construct a likelihood function for the Gaussian distribution on the basis of data. Let me just write out the general term. So if I had observations x1, x2 up to xn, then I will have 1 over root 2 pi sigma squared e to the minus x1 minus mu squared over 2 sigma squared times if they're all independent. So I've got x1 here, and the dot, dot, dot means that I plug x2, 3, 4, 5, 6, 7, all the way up to xn. Can you see how I'm just multiplying all these guys together? You happy with that? I'm going to introduce some new notation. This is like, you've seen the notation sigma for the sum. This is just, instead of adding them all together, you multiply them all together. Yeah? Bit of a mouthful, but there it is. All right. Now I'm going to consider how do I do this? No, I'm just going to remind you that e to the x times e to the y equals e to the x plus y. You know that. I'm going to remind you that e to the x1 plus x2 plus x3 equals e to the x1 times e to the x2 times e to the x3. You know that? I'm going to remind you that e to the sigma xi equals the product over I of e to the xi. You happy with that? Because when we add the superscript, when we add the exponential, we multiplied the values. Yeah, it's just, there are different ways of saying the same thing. Are you happy? Is anybody not happy? And now I'm going to use this in reverse. I'm going to use this one here equals this one here. In fact, I'm just going to think about this term here. As far as the product is concerned, I've got how many copies of this? I've got n copies of this one all multiplied together. Yeah? And I've got n copies of this one. So it's equal to 1 over root 2 pi sigma squared to the power n. Why is it to the power n? Because this term is the same for all of them separately. All right? And I'm multiplying them all together, which is a power. That's what powers are. You multiply them together. Times e to the minus sum xi minus mu squared over 2 sigma squared. Using that formula here. This product here is that product there. I've done this term here already. I'm looking at the exponential. And to multiply exponentials, you add up on here. To multiply exponentials, you add up the exponent. To multiply, oh, it's the other way around. To multiply exponentials, you add here. So these sums turn into these products here. That's why it's useful. That's why logs work. And now I'm going to take logs. Taking logs of this, remember that's to the power a half, or to the power minus a half. So I've got minus a half n, which is this one here. So the power, that power turns into this, and I'm multiplying by minus a half because I've got to the power minus a half here, because it's 1 over the square root, yeah, of 2 pi sigma squared. Minus sigma all right. Because the log of that is just that. The log of e to the x is just x. Yeah? You need to revise your logs. You're looking at me as if you, yeah, you need to revise logs. Well, that's great. This is great. But complicated. What do I do when things get complicated? I use R. So I'm not going to forget the formulas. I think it's important to know while I'm doing the numerical work that there are formulas underneath it. So what I'm going to do is mix and match the algebra with R helping me. I'm going to use R to evaluate this lot. So I'm going to get some data. Actually, I'm going to say x becomes our norm. We know that the true mean is 0, and the true variance is equal to 1. Are we happy on that? So what I'm going to do is I'm going to use R what am I going to do with it? To calculate the probability of data given mu and sigma squared equals the likelihood. And the log of this equals this thing here. All right? So I'm not going to bother with all that. Well, I am going to, in the back of my mind, I've got, well, there's a formula underneath there, and that's what R is evaluating. So let's just take a guess. How do I evaluate the probability? Let's just take a guess. Let's just take a guess that mu equals 0.6 and sigma equals 1.5. We know that the true value equals 0 and sigma squared equals 1. Those are the true values because they were the defaults in our norm. Yeah? So, but we're just going to guess these. And it's devastatingly obvious. Watch. D norm, x, mean, right, D norm, x, mean equals, what did I say? 0.6. Why am I guessing 0.6? Because I felt like it. Comma, standard deviation equals 1.5. These numbers here, if I draw it for you, oh, I've lost my x. Blast. Call it XX. There's my Gaussian curve, which I've shown you 1,000 times. D norm gives me, sorry. Start that again. Get myself tangled up. Let me explain what I've done. Here's my Gaussian. These vertical lines are at my observation. So there's one at minus 0. There it is. What's the biggest one? The biggest one's 1 point something, which is there. So I've drawn lines. D norm gives me these vertical lines here, which is the probability of having the observations. And what we're trying to do is evaluate that. But the data is fixed because I've generated it. It's written on the wall. I'm not going to change it, even though I overwrote it by mistake. But I am going to fool around with these two guys here.